Uh, so I guess I'll get started.
Yeah, go ahead, introduce yourself and go
All
forth.
right. So, okay, good. Looks like everything started up well. All right, so my name is Jeffball. I'm going to give a talk on embedded device, ROP, tips and tricks. It's just kind of a little case study into some IoT exploitation that I've done and how you can kind of turn a Stack Overflow into kind of a command injection exploit, and then port that into an entire fleet of products that all share a common base. And so we're going to look into how to find gadgets, how to automate it a little bit, and then look at some techniques that will let us use a set of gadget across a bunch of devices. So first, the obligatory intro slide. Like I mentioned, my name is Jeffball. I am a senior security researcher at GRIM, hence the GRIM shirt. There's my Twitter handle and my GitHub page, and then I'm also a member of the 9for9 DEF CON group. So, and then next is the obligatory motivational slide. So why do we care about IoT? Why look at this instead of something else? Well, and a lot of times there's good reasons. This is kind of a bad reason. It's easy and I'm lazy. So if you're going to look at something like a web browser, you're going to need to spend a lot of time getting up to speed. And it's also a very popular target, so there's lots of people looking into it. If you just want something that's fun and it's not very hard, looking at IoT is one of the more satisfying things. And so when it came for me to do some side work, like this project, I thought, oh, I'll just play with some routers. Then this kind of gets into, well, why is it easy? Well, they're not very good at coding, and these devices are also cheaply made, so generally they don't have a ton of money in the budget for it. Additionally, they don't use modern protections like stack cookies. Stack cookies were made 20 years ago or 15 years ago, I don't remember the date offhand, but they're pretty much in all modern software. So if you have a generic Stack Overflow, it's non-exploitable. In Netgear's case, they don't use them. Out of the 762 firmware images that have the vulnerability that I've looked at, only 3 have stack cookies. And in fact, it's not the 3 latest. They had 3 versions, 2 different devices had stack cookies, and then in later revisions removed them. And so at one point they had it right, and then they went backwards. And that's just something that makes it easier because all modern software generally uses that. Additionally, other protections like write or execute aren't on sometimes for MIPS devices generally. So you can just jump right into your stack, which is something you haven't been able to do in most modern software for 15+ years. Once again, there's no ASLR or there's very poorly done ASLR. And so you don't have to work to try and leak an address. You can just know what the addresses are because they don't change. And so all of those things combined make it just a easier target than some more modern software. And this talk specifically, I'm going to talk about kind of ways to exploit multiple devices that all have the same vulnerability. And so in Netgear's case, they have 79 or 78 devices that all share the same code base. And so because of that, they all have the same vulnerability. And we're going to look into what that vulnerability is and how we can reuse parts of the exploit across the entire fleet of devices. So this is the target that I started with. It's the Netgear R7000. It's about a $100 Netgear device. It works with Alexa. It's got some generally nice hardware and supports things like gigabit Wi-Fi, and it's got a pretty decent range. And if it weren't for the firmware, I would actually suggest it as a pretty decent device. However, it's very poorly written in terms of security, and so it's hard to suggest this router for anything other than fun times finding bugs. So generally the process that I start with is to pull out the firmware or download the firmware and unpack it. In Netgear's case, they make it real easy. You can just go to that URL and download all of the firmware for the R7000. Then you can use a tool called binwalk. It just walks through the binary looking for signatures of different files. And in this case, it's found a squashfs file system, which is the root file system on the device. And so you can see we just run that command, and then we get this file system down here. And we can just go, we can pull up the binaries in IDA and start reversing or start testing things. Particularly, I normally start with the web server, because in a lot of these Soho routers, the web server is the main process. It kind of starts everything. When you make changes to the admin page, it'll restart a service with different flags and things like that. And so it's kind of the main binary. And so it's a good target to start with. Additionally, a lot of these manufacturers like Netgear and D-Link and so on, they'll take an open source web server such as mini HTTPD or UHTTPD, and they'll modify it with their own modifications, generally done in a less than secure way. And so what you can do is you can look at reverse their web server in IDA, but still refer back to the original open source software, their source code. And so you can it becomes an easy way to kind of spot all the differences and then audit only the differences. So generally, like I said, just pull down the firmware, unpack it, and then start reversing or start testing things against the router. In this case, we're going to look at one bug. This is the vulnerability. In this code, what it's doing is it's accepting a firmware image, and then it's going to parse it to validate that that firmware image is a good one to apply during a router upgrade. This code is immediately after where it reads from the network. And so it reads from the network and then calls this function prior to doing any type of authentication. And so thus it's a real good target if we could find a vulnerability. And so what we're going to do is I looked at this code and kind of reversed it. You can see we have the user input. It gets passed and it gets checked against this string $$$ This string is just a marker that Netgear's firmwares have that let it know that it's a firmware file and not a user uploading something else that will brick the device. And so it checks that. If our user input passes that, we get down to here where it's going to parse out the user input into some size, recombine those into the size, and then it's going to call memcopy with a user-controlled size with user input onto a stack buffer. And this is kind of like the classic stack buffer overflow. And as this comes right after the call to read from the network, there's no chance for it to do any type of authentication. It does a couple searches of the user input to validate that we're trying to upload a firmware, and then it calls this function without checking any type of authentication. And so this right here is a vulnerability that we found that's a unauthenticated stack buffer overflow. These types of bugs generally don't exist anymore in modern software, but thankfully with the poor coding as it is, the Netgear's routers have this, and we can get to play around with that. So let's just the R7000 is an ARM-based processor, so we can kind of just take a look at the function epilogue here. As you can see, we remove our stack frame and then pop off all the saved registers, but you'll notice there's actually no stack cookies. Going back to kind of what I mentioned before, they don't do any cookies. And so down here we see our stack buffer on the stack frame, and then there's a little bit of padding, and then all the saved register values. And after the saved registers is a saved program counter, or where it's going to return to. And there is no cookie, and so all we need to do is just overflow from one to the other until we get to the saved program counter. We fill in the address we want to go to. And as I had mentioned before, there's no ASLR on the main binaries, and this is true for this case as well. And so ordinarily we would need to leak an address and then try and guess it where we can jump to. But since there's no ASLR, we can jump directly to the binary. And in this case, we're going to call this gadget right here, which is a move the stack pointer into R0. R0 is typically the first argument when calling functions. And then we're going to call system. And so what that does is it's going to load a command from our overflown stack and then call system. And so what we'll do is we'll overflow past the buffer, the padding, all the saved registers, fill in a legitimate program counter, and then immediately after we'll put our command because that stack pointer will now point at the command. And so we can kind of take a look at that real quick. The R7000 is kind of the easy case. And so it's a pretty simple exploit. We've got that gadget right here. And then the command we want to run, which is just a startup telnet on port 8888. Then we generate the buffer we're going to give it, which is we start with that marker that we mentioned before. We fill in the size, which is much bigger than the buffer on the stack. And then we start overflowing all our registers, R4, R5, and so on, till we get to the program counter, where we're going to overflow. Sorry, we're going to overflow with the address of our ROP gadget, which will move the stack pointer into the first argument and call system, and then we put our command. We finish it up with some padding, and then we wrap it inside a web request so that it will make it to the vulnerable code, and then we send it off. We can take a look at how that looks. Sorry. First, we'll just check. And we can't get to telnet on the router. We'll run our exploit. And then now we can get to telnet because our exploit worked. It started telnet on port 8888, and we were able to just log in. And then you can do various things like redirect traffic, change DNS responses to redirect the end clients to a different address. We can also do things like dump the password from the router. And so you can see the digest there is the SHA-256 of the router. And so if we just do you can see the hashes match because the password on my R7000 is password123. And so that's just a couple of things you can do once you've infected the router and you've gotten on there. Just 1 second, I'm going to set up the next demo. All right, so then continuing forward, that's the R7000. It's the easiest case. You've got one gadget and you're done. And so we'll look at some harder cases in the next couple devices. One thing you'll want to do when you're writing this exploit is you're going to want a way to automatically grab the gadgets. As I mentioned before, there's 762 vulnerable firmware images from Netgear. We're going to want to exploit all of them or write an exploit for all of them. And so doing that by hand is very tedious and will take a lot of time. Instead, what we'll do is we'll use some object dumped and grep magic to find the gadget we want. In this case, we're going to dump the assembly of the web server, and we're going to grep for calls to system, and then grep for that instruction, which moves the stack pointer into R0. For all of the ARM devices that were vulnerable to this firmware from Netgear, they all have these easy, simple call system with an argument from the stack point or the command from the stack pointer gadgets. And so we don't really have to do much more than that. The next thing that we're going to want to do also is we're going to want to find out what other devices are vulnerable. And so what we can do is we can just download all of the firmwares from Netgear. It's not very hard once you just have to spider their website. Then you can unpack them using just some using binwalk on all of the images. It'll take a little bit of time, but once it's done, then you can just grep through all of the web servers. In this case, this command here, it calls find to find all of the web servers, which are named HTTPD, and then it will grep looking for that marker that we said inside of the web server. If it has it, that means it's a device that has the same code as our vulnerable R7000. And then we can go and look, does it have vulnerable code? And if so, then we can start the process of writing an exploit for that as well. So now we've got the R7000s done and all ARM devices are done. Well, we still have other devices that we need to write an exploit for. One of the other questions you may be asking is, okay, so we know there's a bunch of devices and a bunch of versions that are vulnerable. Well, we can't just send off any type of exploit to the device because if we don't have the correct gadget, which varies per version and even per device, then we'll crash the web server. And thankfully, Netgear has a very easy way to fingerprint a device. And so you can remotely tell what device you're attacking by browsing to this URL, which doesn't require authentication, so it's particularly bad. If you go to /currentsetting.htm, it will tell you what firmware image it's running, what the device is, and various other information. So what the exploit on GitHub does is it pulls this information and then uses that to automatically pick which firmware image, or to determine which firmware image the targeted device is, and then respond with the corresponding exploit. And so thanks to this endpoint, Netgear has made it very easy to target their routers. All right, well, moving on, the next device we're going to look at is the WGR614v9. It's MIPS instead of ARM, so we obviously can't use the same technique as the ARM device to exploit it, so we'll look at how we'll do that. It's the easy case for ARM, the WGR614. Like the R7000, we're again just going to call a system gadget. You can once again see this is the end of the epilogue, function epilogue, and this is the stack frame. We've got our stack buffer, a little bit of padding, and then the saved registers. In this case, it's S0, S1, S2, S3, a little bit more padding, and then the saved return address. We'll just do the same thing as before. We'll redirect that, and in this case, we have a slightly more complicated gadget, but not much. We're going to jump right to this add instruction where it's adding 30 to the stack pointer and then putting it in the A0 register, which is the MIPS register for the first argument when calling system. So basically, it's going to just put 30 past where the return address is into the command that will then call system. It's a little bit more complicated, but not much. And so we can look at just how that's done. So this is the exploit for the WGR614. We've got that gadget of call system, starting with where it fills in that A0 register. The command this time we need to make slightly different because the WGR614 doesn't actually have the device files necessary to run telnet. And so we need to inject some make node commands which will make those device files. And then after that's done, we can just start telnet as normal. Once again, we've got the little header with our marker and size, and then we once again overflow into the saved registers, fill up the padding, put our ROP gadget for the saved return address, that padding for the 30 bytes that it added to the stack pointer to put into the command, and then we've got our command. We null terminate it, and then we fill in a little bit extra, and again, wrap it inside a web request, and then we're good to go. So we'll send that out it'll get sent out the network, and we'll start our telnet. So once again, we'll try and, is it not on? Oof. Oh, there we go. Just takes a little bit to turn on. All right, we can see we can't get to telnet on port 8800. So we will fire off the exploit. And then now we can get to telnet on port because we've injected that command. And so once again, we can get on to, we can dump the NVRAM on this device. It actually doesn't hash the passwords, so we can just see my password for the web server. We could also do other things again, like redirect traffic or modify DNS records responses, or basically just take over the router and do whatever we want on it. Just going to set up the next one. So what I'm doing there is I have a network power switch, and I'm just turning off and on the various routers that I have demos for. I highly recommend anyone who's going to look into this type of research to get one so they're not constantly getting up and having to flick the power on the routers. Essentially just sits on the network. It's got 8 plugs, and I can say turn on or off various ones. Super useful for doing IoT and other hardware-based research. So again, that previous router, it was just a very simple one where we just have to jump to the right place and it'll call system for us. Now we're going to get into kind of some of the harder cases where it's not so obvious on what needs to be done. For this device, the DGN 2200M, we can see the epilogue and the stack buffer. They're pretty much the same. We've got a couple more registers that were overflowing and before we hit the return address, but not much else to see there. The problem with this specific one is, unlike the WGR 614 that we just looked at, there is no call system with a stack buffer gadget in this firmware. And so we've got to kind of manufacture our own. And so the way we'll do that is we'll actually call system. It won't be called from with a stack buffer. It'll actually be filled in from S0, which is one of the registers that we've overflown into. So we can control the command pointer that it calls system with. However, because we don't know where the stack is, because on this device it does actually randomize the stack, we won't know the location of it unless we don't know where our command is in memory. And so what we're going to do is here, first we'll take a look at the system function to see what this is doing. So what we'll do is we will call system with the value null or 0. It'll jump into this. This is the libc on the DGN 2200M. But you don't have to actually look at this a ton, but all you need to do is really look here. At this instruction, it's going to branch if A0 is not equal to null. In that case that we fill in null, it will just immediately go to this branch, which will take us down here, which will take us to the end of the function, and it'll just return right away. And so basically, if we call system with a null pointer, it just returns, which makes sense because there isn't really much to do in system if you don't pass it a command. However, and so what is the point of doing that? Well, on MIPS, when it goes to call a function, what it's actually doing is it loads the address of the function. That's what the LA instruction is, into T9, and then it's going to call the T9 register. That's the calling convention on Linux for MIPS devices. It's expected that a T9 will always hold the address you're going to call. And so in this case, it loads T9, it calls T9, and then since we passed null, it returns right away without calling any other functions. And so T9 still points to system. And so then, since we picked a call to system that's at the end of a function, we just go immediately into the next gadget. And since we can overflow all of this, we can set up a call to a second gadget. And so what we'll do is we'll actually call memset, because memset is typically performed on a buffer, a lot of times which that's on the stack. And as you can see here, what it's actually going to do is it's going to load the first argument with A0 with 19 bytes after the stack. And then it's going to call T9. Since we're jumping past the load of memset into the T9 register, T9 is still going to be set to system. And so the way it'll work is we'll set this first gadget, it'll load T9 to system, it'll call system, return immediately with doing nothing, and then the second gadget will jump right down to this instruction where it calls memset. But however, T9 will still be set to system, and we'll get our call to system with a controlled argument that we want. And we can take a look at how that's done in our exploit. So the first gadget will be calling that system at the end of a function, and then the next one calls memset, which is actually a call to system. Once again, we need to make the device files, and so we'll see our marker. And now what we do is, the only difference is what you'll see here is, rather than overflowing an arbitrary value into S0, we want to put 4 zeros or null, so that S0 becomes null, which then translates into a call to system with null. We've got our gadgets, and then the command, and that 19 bytes of hex, or 19 bytes of buffer. So we can just take a look at how that looks. And again, it works, and we get onto the router. Not much to see there. Again, you can do all the same things as with the other routers, but I'm running out of time, so we'll just move a little bit quicker. And then, so that's that case. And then we're left with the most complicated case, which is the WNDR 3700 V3 and a lot of the other devices that Netgear had. Thankfully, while it's the most complicated, it's not too overly complicated. It just involves the use of the frame pointer. So on this compiler, rather than only using a stack pointer, it also uses a frame pointer. How that becomes troublesome, you can kind of see here, is at the end of the vulnerable function, it's going to overflow the saved frame pointer value, and thus the frame pointer will point to whatever we control. We don't know where the stack is in memory, and so we can't point it at the stack. Our overflow will overflow that value, and then when we go to use a call system gadget, however, we end up with the problem of the frame pointer is used to load that first argument. However, since we overflowed it, we don't know where to point it, and if we try to do that, it will crash. And so we need to somehow fix the frame pointer so it points at the stack, and then we can call system. We can kind of look at here. Here's an instance of a gadget. It's rather long because there aren't too many where in the code that fixes the frame pointer, but here's a gadget that does. First, it's going to copy the stack pointer back to the frame pointer, and then it's going to load a buffer that's 25 bytes past the stack pointer into the first argument and call memset. However, we need to call system, so we kind of need to look into what it means to actually load the address of memset. So let's, on the next slide, we can kind of drill down into that. On the left, I've been showing screenshots of IDA because IDA simplifies it a little bit. But what that load address is actually doing is this load word T9. IDA translates it to make it the code a little bit easier to read. And so what we see here in the middle instruction is the load word, that's LW, T9, the T9 register, 29,000 bytes before the GP register. And so it's going to read from memory 29,000 bytes before the GP register, and then store that to T9. We can take a look over at how that's done in IDA. Essentially, the GP register points around an area that is on the left here, we can see, or in IDA, we can see it. It's just a big table of function pointers that the Linux loader, runtime loader, fills in the values to. And so in this case, it's filling in the value of the address of system. The reason that's done is at compile time, you don't know the address of system because there's ASLR, the library will move around. And so that address needs to get filled at runtime by the loader. And by having this giant table, we can make sure our code doesn't have to change so that we can still call system at the right address. And so when it does that load address or that load word from GP, it's actually reading into this table and reading the value that the runtime loader filled in. And so in this case, it points to system, just 29,000 before the GP register. However, if we want, in a different case, the one that we were looking at before, it's pointing to this memset pointer, which holds the address of memset. And so the basic technique you can probably figure out from here is we're going to modify the GP register with the offset between memset and system. So that when the code thinks it's loading a pointer to memset, it's actually going to load a pointer to system. And the way we'll do that is we'll call this little gadget down here at the bottom, which just simply loads GP from the stack overflow, which is because there's no randomization in the main binary, we know what the GP value is going to be. And then we'll load it with an incorrect value, which will turn the memset on this gadget into a call to system. And we can kind of take a look at how that's done. Nope, I think I forgot to turn a new one on. Let me just turn the last demo on. All right, it'll probably take a sec. So this is the exploit for the WNDR 3700v3. This first value right here is, this is the original value of GP, and then we're going to adjust it by 72C bytes because that's the difference between memset and system. And so once we load this value, all memset calls will point to system. This next gadget is the one that loads the GP value from our stack overflow, and then we have that last one that fixes the frame pointer and calls memset with a stack buffer. There's not much to see here, too much to see here, other than we filled in our ROP gadgets with our GP value, and then the second ROP gadget, and we put our command, and then again wrap it inside of a web request and send it out. See if our device is up. No, it's not. All right, well then we've got a couple minutes to kill. why don't we just take a look at the web request? Essentially, we're just posting to upgrade check. It's got to have certain fields, the Netgear code. It actually uses the stir function, so it's not actually parsing this web request. It's just looking to make sure we have actual strings. That's why we don't actually have to form a valid header here. We can just make sure that string is in there, and the string will work. Same with this content disposition. It doesn't actually need to be a valid value. It just needs to be in the request. All right, it looks like the WNDR 3700 is up, so we can try. As we can see, telnet is not open. We'll run our little exploit, and then we can get on the device. And you can actually see telnet right there running in the output PS. We could again do all of the various types of things that you would do if you could with an infected router. And so, kind of just summing up, those 4 techniques are basically enough to exploit the entire line of vulnerable devices from Netgear. They're easily automated. I showed one of the automated techniques for the first one, but with the MIPS and the later ones, you can also automate them. The second link there has tools to automate them and find the gadgets using IDA-Python. So that's kind of the talk. If there's any questions now, I could take them. If you want more information, our blog that we wrote up about this and the exploit and the tools to support this type of exploitation and vulnerability analysis are at that second link.
Oh, awesome. Hey, Bryson. So do we have a little bit of time for Q&A? So the first one was from a wee bit ago, but you mentioned something like ASLR half existing. Can you talk a little bit more about that real quick?
Yeah, all right. So ASLR, so on Linux, there's a couple different things. ASLR, I guess I should have put it, it does exist on some devices. Again, there's 79 devices that were vulnerable, spans a range of 13 or 14 years. So earlier ones didn't have any ASLR at all. They loaded the libraries at the same address every reboot and every time they loaded. Later ones, they turned on what's known as kind of ASLR. The libraries get randomized, but they didn't compile their binaries PI, position independent executables. And that's needed on Linux in order to load the main binary at a randomized address. And so while libc might be randomized and the stack might be randomized, but the main binary, or HTTPD, which is the one we're exploiting, it's always at the same address. And so when I showed screenshots of the gadgets, this is inside of HTTPD. And so its address is always 3CFB4, and we can always jump there. But if I were to try and find a gadget inside libc for the R7000, which does have ASLR, that's randomized. And so the problem with that is if you don't do ASLR to everything, I can find gadgets in the things that aren't randomized. And so as we've seen, I don't need the gadgets in libc and the other libraries because I have gadgets in the web server. So that's kind of what I meant by bad ASLR or no ASLR. I kind of fused the two terms of PI because I didn't really want to get into it too much. But by bad ASLR, I mean they don't compile them PI.
Perfect. 2 more questions. So the first one is from a reverser or exploit developer perspective. You've now presented a lot of really great information. Do you have any recommendations on how somebody could take what you've just presented on and do something themselves, or another good place to look for this sort of stuff or experiment? Like, what would be a practical exercise based off of what you've just demonstrated for someone who wants to learn to do this stuff? So
let me just pull this up. So I would generally recommend going to get an IO2. What's the name of it? There's a really, really bad smart plug, DSPW W215, I think it is. You can get a version A of it. It's really bad. There's every single stir copy is an exploit, or is a vulnerability. Yeah. So All right, not really
Cool.
all of them, but if you go and look and just cross-reference in IDA on um, stir copies, like half of them are exploits, and it'll be things like there'll be a stir compare with the word cookies, and then immediately after is a stir copy that's a vulnerability. Um, and so one good thing you can do is you can just download Ghidra or IDA and pick a old firmware or a firmware that's known to be vulnerable like this, and just go about reversing it. If you can't buy the device because there's either money or they're hard to find the specific model that you're testing, you can generally try emulating them inside of a VM that runs the same architecture. Some devices it'll work, other ones it's a little bit hard because of the specific instruction set that the firmware expects. This one I know runs inside of a QEMU MIPS device relatively easily. But yeah, just going and looking at some of these devices or these easy targets is a nice way to get started. So hopefully that helped. Ghidra, and if you have a Hexrays or IDA, that's also a good place to start.
Awesome. And then the last question is, there's from a non-exploit researcher perspective, as just a, a consumer that may or may not have a Netgear device, well, I'm sad now. What should I do? Professional security researcher?
Don't buy Netgear or D-Link. I generally try to run the open source versions because they're made by people who care instead of people who want to make the cheapest device. So like I said before, the hardware on this device is actually pretty good in terms of performance. And so one of the things you can do is you can take something like, I think the R6700, if you have one of those, is again also pretty good hardware, and then run OpenWRT or DDWRT. I don't know if the R7000 specifically supports it, but I'm pretty sure the R67 does. But again, don't buy this just for that. I typically look on those DDWRT, ASUS Merlin, a couple other different open source ones for what they're supported or the most supported devices, and then purchase that for my networks.
Perfect.